Hello everyone, welcome to my short presentation on differentials. Okay, so differentials. Recall when we studied the precise definition of the limit, and if you've forgotten, this was the definition of the limit that used the epsilon and delta notation. When I presented that definition, I tried to get you to think about delta as the measurement error in the input variable and epsilon as the measurement error in the output variable of the function. With differentials, we can use the input error to estimate the output error of a function. So let's say that we have a function y is equal to f of x and that this function is differentiable over some open interval. When we go to find the differential, we will take the derivative like we normally would, but we're now going to write our notation as such. We're going to have dy is equal to f prime of x times dx. So that's a little bit differently than saying dy over dx is equal to f prime of x. So we just have a new different notation. Now let's take a look at an example as to how that's actually going to calculate. So if I have the function y is equal to x squared, when I take the differential, the y becomes dy. Taking the derivative of x squared, that gives me a 2 times x, and then I write the dx after that. So this is just the x squared function that we're taking the derivative of, but this works for anything that you can take the derivative of. So all of our derivative rules are still going to be applicable. Alright, now that's just the way in which differentials differ from the derivative. It's just the notation. But let's take a look at how we can use these differentials that we calculated in this first example. So if I was to take 3 and plug it into the equation y is equal to x squared, that would give me y is equal to 9. So what that means is if x is exactly 3, then y will be exactly 9. But in a real-world setting, when you measure something, you might not have exactly 3. It might be 3.005 or something like that. It's going to be slightly off of 3. So if there is some measurement error in the x, how much would the y value be off by? So let's get some notation down. Delta x, we're going to use that for the error in the x value, how much the x might be off by. And delta y is going to be the error in the y value. We can then use differentials to approximate the value of delta y when we have the value of delta x. In other words, if we know the input error, we can use that to approximate the output error. So how is this done? Well, after taking the differentials, we're going to let delta x equal to dx, and that will mean that delta y is going to be approximately dy. So let's see that in action. So from the previous example, we had y is equal to x squared. When we took the differential, that gives us dy is equal to 2x times dx. So let's find out what error we're going to get when x is equal to 3 and our measurement error, delta x, is equal to 0.1. So my dx is equal to delta x, which is 0.1. X is equal to 3. So plugging that into our differential, that gives us dy is equal to 2 times x, which is 3, times my dx, which is 0.6. And that calculates to a 0.6. So the error in the y value when x is equal to 3 is going to be approximately 0.6. So when x is equal to 3 and the measurement error in x is off by 0.1, then we can expect the error in y to be around 0.6. So here's a question: how accurate is this going to be? So in our example that we used, we had y is equal to x squared. when x is equal to 3 and delta x is equal to 0.1, let's actually calculate what the error would be if I plugged in 3.1 for x. So if I plug in 3.1 for x, that gives me a y value of 9.61. So if x is exactly 3.1, then the y value is exactly 9.61. And then if I subtract the 9.61 and the 9, that gives me a 0.61. So the delta y between 3 and 3.1 is exactly 0.61. And that is pretty close to the estimate we got for our differential, which was 0.6. Now we're going to use this concept for another interesting example, and that is approximating the square root of 4.1. So I'm going to use differentials to approximate the square root of 4.1. Since we're doing square roots, I'm going to use the function y is equal to the square root of x. Now I'm going to rewrite that y equal to square root of x in a derivative-friendly format. So that's y is equal to x to the 1/2 exponent. Calculating our differential, that's going to give us dy is equal to 1/2 x to the negative 1/2 exponent followed by dx. Or equivalently, dy is equal to 1 over 2 times the square root of x, all of that times dx. Well, we know that the square root of 4 is equal to 2, so that's an easy value for us for square roots. The square root of 4 is equal to 2, but we want to take the square root of 4.1. So we're looking at delta x is going to be the difference between 4.1 and 4, which is a 0.1. So 4 is our value that we can take the square root of, and 4.1 is the value we're going to try to approximate. So we find the distance between those, and that gives us our delta x. So now we're going to plug 4 in for x, and we're going to plug in 0.1 for my delta x, and we're going to put that into our differential. So plugging those into our differential, we get 1 over 2 times the square root of 4, and then all that is times a 0.1, which ends up giving us a 0.1 divided by 4, which calculates to a 0.025. So when x is equal to 4 and my dx is equal to 0.1, that means the y value is going to be off by approximately 0.25. So to calculate the square root of 4.1, that's going to be approximately the square root of 4 plus the amount that it was off by, which was 0.025. So adding those together, that gives me 2 plus 0.025, which gives me 2.025. Now, those calculations could actually be done relatively easy with pencil and paper. It doesn't really require a lot of computation time or power to actually do that particular arithmetic. But I'm kind of curious as to how close that approximation is to what a calculator would spit out, down to 8 decimal points or so. So when I used my calculator, I took it down to 4 places. So using my calculator, I got the square root of 4.1. That's approximately equal to 2.0248. And if I rounded that answer to 3 places, I get what I would have gotten by using differentials to approximate the square root of 4.1. Well, thank you for viewing this presentation, and I will see you next time.